Linear and session types tackle the most challenging protocol problems, ensuring that resources are used exactly once, or that paired operations like acquire or release are properly balanced. The fundamental insight is that some values should be consumed by operations rather than just used. In traditional type systems, when you pass an object to a method, you still have the object afterwards. You can call more methods on it, pass it to other functions, or store it for later use. This aliasing capability is useful for most programming tasks, but it creates problems for resource management protocols. Linear types change this by tracking ownership and consumption. When you pass a linear value to a function, that value is moved. You no longer have access to it. The function that receives the value becomes its new owner and is responsible for either consuming it or passing it on. This ownership transfer is tracked by the type system and enforced at compile time. In our transaction example, the transaction active type represents a transaction that can be consumed by either commit or rollback. When you call transaction.commit, the self parameter is consumed. The method takes ownership of the transaction and the caller no longer has access to it. The method returns a transaction done, representing the fact that the transaction has been finalized. The key insight is that the original transaction variable is no longer accessible after the commit call. If you try to use it again, the compiler gives you an error saying the value has been moved. This makes double commit bugs impossible, not because of runtime checks or defensive programming, but because the type system prevents you from even referring to the consumed transaction. This ownership tracking enables several important guarantees. First, resources cannot be used after they are released. The move semantics ensure that consumed resources are no longer accessible. Second, resources cannot be leaked. If you have a linear resource, you must eventually consume it or the program won't compile. Third, resources cannot be used concurrently. Since only one reference can exist at a time, there are no race conditions. The transaction done return type serves an important purpose too. It represents proof that the transaction was properly handled. You might need to pass this proof to other parts of your system to demonstrate that cleanup was performed. The type system ensures that this proof can only be obtained by actually consuming the resource properly. Session types extend linear types to model communication protocols. Instead of tracking resource consumption, they track the valid message exchange patterns in concurrent systems. A session type might specify that after sending a request message, you must receive either a success or error response before sending another request. The type system ensures that both sides of the communication channel follow the protocol correctly. Now, linear types require language support for move semantics and ownership tracking. Rust provides this natively through its ownership system. Other languages can simulate linear types through careful API design and convention, but without compiler enforcement of the move semantics. The challenge with linear types is that they change how you think about program structure. Instead of objects that you can use repeatedly, you work with resources that flow through your program and get transformed or consumed along the way. This can make some programming patterns more difficult, but it provides unmatched guarantees for resource safety and protocol correctness. The key to successful protocol design is matching your technique to your specific problem characteristics. This isn't just about picking your favorite approach. Each technique has distinct strengths and weaknesses that make it suitable for different scenarios. Before choosing a technique, analyze your protocol along these dimensions. State complexity. How many distinct states does your protocol have? Simple protocols with 2 to 4 states work well with fluent interfaces. Complex protocols with 10 plus states benefit from phantom type parameters or code generation. Transition patterns. Are your transitions linear, like A to B to C, or do they form a complex graph with cycles and branches? Linear patterns suit fluent interfaces and stage builders. Complex graphs need phantom types or session types. Value dependencies. Does your protocol constraint depend on runtime values or just on which methods have been called? Pure state based protocols work with the first three techniques. Value dependent protocols require refinement types. Usage patterns. Is this a construction protocol that is build once, use forever, or a usage protocol, which is an ongoing interaction? Construction protocols benefit from stage builders. Usage protocols need state tracking approaches. Error likelihood. What mistakes are users most likely to make? If it's forgot to call required method, use linear types. If it's called methods in wrong order, use fluent interfaces. If it's provided invalid values, use refinement types. Your choice is also constrained by practical considerations. Language support, for example. Now, TypeScript excels at fluent interfaces and phantom types. Rust provides excellent linear types. Java works well with fluent interfaces and staged builders. Haskell enables refinement types through liquid Haskell. Team expertise. More advanced techniques require team members who understand the underlying concepts. Phantom types need developers comfortable with generics. Refinement types require some formal methods background. Tooling, tooling integration. Consider how well your IDE and build tools support each approach. Fluent interfaces provide excellent autocomplete. Phantom types may produce confusing error messages. Refinement types require specialized tooling. Migration path. If you're retrofitting an existing API, Fluent interfaces and phantom types can often wrap existing implementation. Stage builders and linear types usually require complete rewrite.